So in this talk, I will introduce two different tools. The first one is tau, and the other is the extreme scale scientific software stack, E4S. So the tau performance system is a versatile tool. It can show you where your application spends its time. You can use it to optimize your applications. It supports both profiling and tracing modes of performance measurement. It has 3 different components of instrumentation or adding hooks to your program, measurement for performing profiling or tracing, and analysis where you can view the performance data generated by tau in profile files with our tools such as Prof, or in tracing mode with third-party tools such as Vampire, a commercial trace visualizer, or JumpShot, or even the Chrome trace browser. So, if you're wondering, what can tau do for you? Now, how do you use tau? What kind of information can it produce? At the highest level, we can find out how much time was spent in each routine. We can see what was the time spent in basic blocks or loops. And even at the statement level, you can see how much time was spent in OpenMP loops. You can see how much time was spent in the kernel execution on the GPUs. You can look at hardware performance counters instead of time, so you could see metrics such as floating point instructions, level 1, level 2 data cache misses, executed at the level of loops, at the level of routines. You can look at the memory usage of your code. You're probably wondering, when is memory allocated? How much memory did my application allocate? Where did it do that? How much was deallocated? Were there any memory leaks? Was memory being used in an inappropriate way? Like, were you exceeding the bounds of arrays that were allocated? What is the memory footprint of my application? What is the max memory usage? And if I add up the stack, heap, data, BSS, text, all of that, what is the max high water mark of memory usage in my application? You can find that out with tau. You can look at the energy usage of your code. You can look at the I/O. You're probably wondering, which files did my application access on which file systems? What was the data transfer rate in megabytes per second? What was the bandwidth? What was the volume of data accessed by my code? You can see all that. You can look at the scalability of your application as well. As the number of cores increase, where is the application spending its time? What is the runtime breakdown of your code? We have tools such as Perf Explorer that can connect to a database, the TauDB, and look at cross-experiment analysis studies. So at the core of it, there are 2 different modes of measurement. One is profiling, which tells you the summary statistics, okay, the total time taken in your application. It shows you how much time was spent in each routine, at the loop level, at the statement level. But tracing can show you when and where the events take place along a timeline. Traces are generated by tau, and these include timestamped events. So every entry and exit is logged. And you can see exactly what each process was doing along a timeline view. So that's the key difference. Profiles are compact. They show you the total time spent over all invocations. And traces show you the detailed temporal variation of your application. Now, with tau, you have 2 different ways of generating the performance data. One is directly using probes, where entry exits are measured based on an instrumentation hook in your code. So there is an explicit call to a start routine at the entry of a function and a stop routine for that code region. And then we also support sampling, where you take an interrupt periodically. This interrupt can be based on hardware performance counters, it can be based on the wall clock time, but basically you can estimate the time spent in the application based on interrupts. that are encountered in the application. So we have a tool called tau exec. It's a very simple tool to use, and you can use it to preload libraries, like the tau library. What happens is the application is loaded in the memory, but before that, the tau library is loaded, and it has wrapper libraries for MPI, IO, CUDA, and so on, and they intercept these libraries from your application. So if your application is making a call to MPI, tau intercepts that MPI call, and then tau internally calls that MPI routine. And with that, you can measure the time spent in the runtime library layers. You can also look at memory evaluation. But what is interesting is that you don't need to modify your binary in any way. You just launch it with tau exec. Okay? And then you can enable other options in tau, including turning on event-based sampling, so you can see what the rest of the application did. So with this, you can measure a number of different runtimes, whether it is OpenMP, OpenCL, OpenACC, CUDA, and you can also use another tool called tau_python. It behaves very similarly to tau exec, just that you can launch Python applications using tau python. Okay? So there are many different runtime systems that tau supports. These include, of course, for the HPC community, the MPI runtime, and we support the PMPI, profiling MPI wrapper, but also some advanced MPI distributions such as MVAP-H2 support the MPI tools interface. Now this is the MPI-T interface that allows the tools to collaborate with the runtime. They can look at the performance variables that are exported by the MPI runtime. This can give us detailed statistics of the inner workings of the MPI. Like we could look at the memory usage of the MPI runtime. We could look at the congestion at a network interface. We also support control variables that allows you to modify the behavior of the runtime by turning these knobs. So you could change the number of pools of memory buffers, for instance, at runtime using these hooks. So without any modification to your application, tau can collaborate with the MPI runtime and modify those control variables exported by the MVAP-H2 runtime. Tau supports pthread, OpenMP using the OpenMP tools interface. The OMPT 5.0 interface is now implemented in tools like compilers like Intel compilers and Clang compilers. Clang 8.0 compilers are available on PPC64LE, and we have used it on IBM systems for looking at the interface, and you can use these together with MPI. You have support for OpenACC, instrumentation API, we have support for OpenCL, CUDA, where we use the CUDA profiling tools interface with CUDA 10.2, for instance. You can track the data transfers between the host and the GPU. You can track access to shared memory between the host and the GPU. We have support for ROCm, the Cocos profiling interface. Cocos is a very interesting runtime that allows you to address the MPI plus X problem. Whatever is happening on the node level, you can use Cocos as a layer to program, and then we can look at the interface for regions, kernel executions. We can also instrument at the level of Python interpreter without modifying any of your code. In all of these cases, you can just launch the application using tau_exec. And then it interfaces with Cocos, it interfaces with kubectl and gets the hooks for instrumenting your application. And you can see over here that there are a number of different cases. You can look at the performance of an MPI plus OpenMP application, a hybrid application, by inserting the hooks at the MPI level as well as the OpenMP tools interface level. You can look at MPI plus CUDA application using the PMPI plus kubectl interfaces. You can look at other cases like Cocos with OpenMP or Cocos with CUDA backends on IBM. We've done some experiments at Livermore with CUDA being used with Cocos, with MVAP-H2, and you can again transparently intercept all of those calls and see exactly where the kernel executions take place and how much time it takes. You can look at Python with CUDA, MPI with OpenCL. And to use this, if your application is launched with just a.out, you can launch an MPI part with whatever MPI run or S run or a launcher script with just tau exec a.out for just MPI. If you want to intercept the calls to the CUDA profiling tools interface, look at CUDA application performance, you say tau exec-cupti or tau exec-opencl or tau exec-openacc. With OMPT, we have support, like in this case, we have on the IBM system a Clang compiler with OMPT version 5 support, and you can say tau exec-t tags for the configuration. OMPT version 5, Clang, MPI, and then OMPT is enabled using this. There's also some other environment variables that tau exports. In this case, I'm saying track the OpenMP kernels on all the threads by enabling the OMPT support level as full. This is just an example. We have a range of these environment variables that you can set. If you want to track I/O, you say tau exec-IO. To enable sampling, you can just say tau exec-event-based sampling or EBS. You can specify the period, you can specify the overflow count for hardware performance counters and specify which counter to use. You can also specify whether you want to modify the resolution to just the file level to be the coarsest, or the function, or down to the line level. So you can just generate a different volume of data based on that. And when you configure tau, it creates a libtau.so and it puts it in a shared directory which has tags in its name, like the OMPT, V5, and so on. So here are two examples where I configure tau with PAPI or without PAPI, and then I can choose the configuration using the -t parameter over here. If you don't want to launch the application, you can just see a dry run with the -s option. And once you generate the data, you can launch Paraprof. Paraprof is the browser, and here's a 3D profile browser that's integrated in Paraprof. You can see along one axis the MPI ranks, the other axis the functions, and the height is the amount of time or exclusive time spent in that routine. And you can zoom in, zoom out, and you can see basically the shape of your execution. We can use it for HPC and AI workloads. Here is an example of using it with TensorFlow in the case of tau. Here, instead of Python, where I say Python classify mnist.py, I can just say tau_Python and enable sampling with that mnist.py. And then I can launch Paraprof. And here is the manager window that shows the Power 9 processor details, the V100 GPU information. You can look at the context event window, which shows you the execution of the kernels, the allocatable blocks, and detailed information about the extent of variation of this context event. You can look at the actual execution time for that kernel. You can see the other functions in this case. And you can look at the time spent in a given routine. And here is the complete expansion of the template in the TensorFlow code. Other examples like that. And you can see the detailed breakdown of statistics on each thread of execution. And you can track the data transfers. Here you are looking at how much data was transferred between the CPU and the GPU. And look at the exact timings for the CUDA routines overall. Now, how do you install tau? You can download tau from the website. You can configure the program database toolkit, which is a static analysis system for source instrumentation. And then you can install tau like this by configuring it and give external packages. Now we have an easier way to deal with the installation, and that leads me to the second part of my talk. You can use SPAC and E4S. The Extreme Scale Scientific Software Stack is a community effort to provide these open source packages on HPC hardware. It lowers the barriers for installing software. Let's face it, our tools and libraries are getting very complex. They have a complex dependency graph as well. To contend with that complexity, they use SPAC. SPAC is a platform for installing software. And we have built this complete scientific software stack based on SPAC. So it provides bare metal builds as well as container-based distributions. Now, what are containers? A container is a lightweight collection of executable software that encapsulates all the dependencies. Okay? It's based on Linux. It creates a portable software ecosystem. It allows you to install software and nail down the environment. Okay, that is very important. Docker is a common platform for deploying containers, but I'll describe the HPC containers as well. So the key difference between hypervisor-based approaches and other VM-based approaches are that with a container, you have the same kernel as the host. Okay, there are no two kernels running. There is no separate operating system. There is only one OS. Okay, there is only one kernel that's executing, and then you can deploy it with the libraries like this. Now, Docker is not a good fit for HPC systems because of security issues and root access, and there are other solutions that you may want to consider, and these include Shifter, Singularity, Charlie Cloud, and the E4S supports all of these. So here is the overall view of E4S, where we use SPAC as a package manager, and then we create containers that can be deployed with these runtimes. Why SPAC? Well, scientific software is becoming extremely complex. You can see this is an example of Nalu, a code, and this is the dependency graph. Okay, here is another example. This is the deal 2, and you can see all of these packages, whether it's Python or Metis. Here is another R minor, and installing this full dependency graph one by one is really hard for HPC developers. If you make one mistake in one of those components, the whole thing comes crashing down. So SPAC curates that whole process, and even proprietary codes use many open source libraries. So we have this whole ecosystem of tools and libraries that can be easily installed. So you can just do a git clone from the SPAC website. SPAC is available from spac.io, and just say SPAC install tau. Then tau and its dependencies can be easily installed. You can also choose different options. You can say, I want this compiler and not that. I want this MPI version, this pthread library, and so on. So you provide an easy way to install the software. You can say SPAC install tau, and it will install it just with that one command, and it will use the defaults. Now you can specify a custom version. I can say SPAC install tau at 2.29. By the way, this version was just released this week for supercomputing. You can say SPAC install 2.29 version of tau, but use GCC 7.3.0, and there's a percentage. So SPAC understands versions, SPAC understands compilers. That's a key difference. And it can install from source as well as install from binaries. Okay? You can say SPAC install tau with MPI, with Python and pthreads, and it will give a plus minus variants. You can also specify a given version. Because of all the MPI versions that are available, MVAPIC2 being one of the best versions of MPI available for InfiniBand especially, you can say SPAC install tau at 2.29 with GCC 7.3, enable MPI but use MVAPIC2 version 2.3 by using an option which is don't enable the wrapper or path, like an option of MVAPIC2 package. And you can specify this dependency information with SPAC. So this gives you a very versatile platform for installing the software where each spec can be custom configured. You can look at SPAC find command to see what was installed. Now this is an output from the E4S base image for PPC64LE, and I can see exactly which packages are there in the base image, where we have mpitch, we have GCC, we have readline, other tools like this, and you can also use SPAC to generate module files. So this is you can get more information about SPAC from this web page. We have used it to create the release 1.0 of E4S distribution, and we have base containers as well as full-featured containers. And for example, we have 50 full-release ECP software technology products that include MPI, development tools, math libraries, and we have other products that are based on containers that can be launched using these different runtimes, including Singularity. We also have a OVA file that I'll describe. You can also use our SPAC mirrors. So instead of building from a scratch, we have created SPAC build caches, which include binaries of many packages. And you can just point to this mirror at the University of Oregon for the E4S, and then SPAC will use this to install your application. There are over 1,000 different SPAC binaries in this build cache for multiple platforms, and you can see over here, these are the PPC64 CentOS, Red Hat 7.6, and Ubuntu platforms. We also have reproducible container builds. If you don't like what's there in our big image, you can create your custom container. But as a starting point, you can use the base image. And with that base image, you can see a full recipe of this. Like this is for PPC64LE. We have a way to replace the MPI in the base image with a more performant version, which is installed on your system. So if you log into your IBM system, you may have MVAPIC2 GDR, which allows you to access the GPU memory and InfiniBand in a very efficient way. You can build an application with the base container and replace the MPI with the system MVAPIC2 MPI. And you can use the base image and then build upon that. Here are base images posted on Docker Hub, where you can see that there is an ECP E4S tag, and then there is a base image for Ubuntu 18.04, PPC64LE for UBI, which is the Red Hat 7.6, and then CentOS as well. And you can just say Docker pull and the image name. These are all IBM specific images. And here is a build cache for PPC64, where we have created binaries of all of these packages and different versions of the compilers and OSs, and there's like 2.6 GB of disk taken up in the base image. And we are building upon that. We have support for Docker, and you can look at various base images, like you have PPC64 for Ubuntu, and you can get access to that from our E4S webpage. Here is the support for Singularity Containers. in tau, E4S. So you have Singularity containers for the base images for PPC64LE on CentOS, UBI 7, Red Hat, as well as the Ubuntu 18.04. And you can just download this SIMG file, and then you can launch it with Singularity. Note that I used the --NV option when I did a Singularity exec. That enables access to the GPUs. So you can use these images with GPUs and then access the NVIDIA V100 GPUs on your system. SPAC find and other commands can be used once you launch this with the EDC bash RC. So one of the interesting issues that we face is that applications built with MPI in the container can be launched on HPC machines where you can replace the MPI with the system MPI. So you use fast internode communication using the system MPI like the MapH2 install. And then the application and data can be external to the E4S container, and the programming models, runtimes, compilers, and tools can be inside the container, and then we use this MPitch API compatibility layer and build a single binary that can run on multiple machines. And here is a virtual box image that shows all of these different runtimes. If you just want to learn more about these container runtimes and use the containers, you can just download this OVA file and use it. It's also available on AWS. And our future work includes work on GPUs, improved support for GPUs and visualization tools, continuous integration testing, facility deployments, scalable startup research with full-featured super containers project, and improving the launch of MPI applications so it's more easy to launch these. If you would like to learn more about tau and E4S, I would like to invite you for a talk at the Ohio State University OSU booth, number 2096. It will be held on Tuesday, 4 to 4:30 p.m. on the interaction between MVAPitch and tau and performance engineering of codes. And we have a BOF for E4S. We have a Canopy HPC workshop at Supercomputing. There is also container computing for HPC and scientific workflows tutorial on Sunday. I hope to see you at these sessions. I would like to thank the Exascale Computing Project for sponsoring both of these projects, and our other sponsors, including the Department of Energy, the Oak Ridge National Labs, Argonne, Office of Science, Exascale Computing Project, the SIDAC LBL, the Tri-Labs, Los Alamos, Livermore, Sandia, PNNL, Battelle, Department of Defense, National Science Foundation, NASA, CEA in France, and our partners at the University of Oregon, the Ohio State University, Paratools, and the University of Tennessee, Knoxville. Thank you.